on A. And of course, point 1 over here means what? Only in history class he receives an A, not in math class. And on the other hand, here point 2 means only in math class he receives an A, not in history class. Example 4 sounds a little less familiar, okay? By the way, this is my home office, and we converted it to studio for this time. Okay, I really appreciate, having a board and everything. I can do it at home, and I try to really recreate the environment that we always had. Well, so I hope you don't feel really strange about this. Yeah. Resource availability. A factory needs 2 raw materials in order to operate. Okay? The probability of not having an adequate supply of material A is 0.05. So they need 2 kinds of raw material. Material A and material B. They have to have an adequate supply of both of them, to operate the factory. But sometimes, well, unfortunate case that not having an adequate supply of material A is 0.05. So I'm going to put it this way. Not having enough is 0.05. So this A means not having enough, okay? And on the other hand, raw material B also sometimes causes a problem, that is 0.03. So this one is not a good one, okay? So this is problematic. Those are the problems they have. Our study determines that the probability of not having an adequate supply, it's not solely, okay? Supply of material A and B is 0.01. So this time both are inadequate, then of course definitely they cannot operate that. 0.01. What proportion of the time can the factory operate? Okay, so those are the problems here. It's not a good time, it's a bad time, downtime. Okay, so over here we are going to draw a Venn diagram. So material A is not adequate 5% of the time, and the material B is not adequate 3% of the time, and here OA and B both, that is 0.01. So what do you think over here? They have a problem 5% of the time and 3% of the time, but 1% of the time it causes by both of them. So anyhow, even just one material is not enough, then they cannot operate, so they cannot include this one 2 times over here. Okay, so what we have to do, here is 0.04, here is 0.02, correct? So these are the problematic times. Well, what is a good time so that you can operate the factory? That is what? Outside these circles. Okay, so this is many times we have an association with in our minds that those circles indicate like a good thing to happen, but this is not. Okay, so these things are operable over here. Operable, these outside. So what do you have? These things together add up to 0.7, correct? 0.07. So this operable time means 1 minus Okay, add them up. 0.04 plus 0.01 plus 0.02. Therefore, 1 minus 0.07, which is 0.93. So how can you say? Yes, 0.93, that is 93% of the time. Yes, the 93% of the time the factory is operable. Okay, so this is 0.93. Okay, I hope you understand this question. Okay, just the only thing is inside these circles are the bad situations that they do not operate. They cannot operate the factory. Alright, probability distribution for the number of boys in 2 children families. So, in order to consider this case, yes, those families have 2 children, okay, and we are going to assume that, well, having a boy or having a girl, those things are like equally likely to happen. So in other words, if you see a lady who is pregnant, that she is going to have a boy or a girl, it's just 50-50 chance. Biologically, they said it's not really, because having a boy has just a slightly higher than having a girl. But that is only biologically, but you know, it's just in math world, just we take it as like a 50-50 chance. Okay. Here there are 2 children, so example 4. Oh, example 4, there are 2 example 4s, so I'm not going to say that, okay. 2 children families. Observe the genders and the birth orders in 2 child families and calculate the probabilities of having just no boys, having 1 boy, and having 2 boys. Okay, so 2 children, so they have 2, but the gender mixes, yes, we have to calculate that. Okay, so we want to calculate having no boys in the family, probability that just 1 boy, and the probability that having 2 boys. So how do we start this one? Well, we are going to take this sample space as we'll consider both of them. Both is that gender and the birth order. You think about both of them. So let's say here the first case can be girl and girl. Girl and girl, and the girl and the boy. And the boy and girl is different thing, right? Because, so let's say this is the left one is older one. Older one is a girl, this one is older one is a boy. Even though same gender mix 1 and 1, okay, 1 each. The last thing over here is boy and boy. You see, there are 4 different possible outcomes over here, and the probability for each one is 1/4, because each one has a probability of just having 1/2. So this is 1/4, 1/4, and 1/4. So probability that having no boys, I do not see any B is here, B is here, B is here. Only one case, 2 girls. So this is 1/4. Having 1 boy, having one boy, well, this case and this case, and these two are, well, mutually exclusive because we counted the birth order, correct? Okay, so this is 1/4 and 1/4, that gives you 1/2. Oh, it's not a good writing. So therefore the final answer is 1/2. Having two boys, boy and boy, so that is just one case out of 4. Okay. The common mistake over here is you are going to make a sample space of just 3 of this because, oh, one boy and one girl. Okay? But if you use birth order, then you are not going to make any kind of mistake over here. Okay. Probability associated with the roll of a pair of dice. Okay. It sounds familiar? Yes, you did some problem like this before the exam. So example 5. Suppose that we roll a red die and a green die and observe the numbers on the sides that face upward. Okay. Calculate the probability of the elementary events, just event with just a single outcome. Okay, so you have a red die and the green die. Red and the green die. Each one has a possibility of from having 1 to 6 and 1 to 6. That's why it is convenient to say here the sample space is 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6. So each time the just one is on the red die, and on the other hand the green die, all different possibilities from 1 to 6. We will just organize like this so that we do not skip anything and we do not repeat anything. So this one, 2 1, 2 2, 2 6. So 6 1, 6 2. The last row shows just 6 occurs on red die all the time, but the green die has all different possibilities. So each elementary event, each one is an elementary event, okay? This is just basic term. So that is 1 over 36 because there are 36 outcomes in the sample space, just one case out of 36. Calculate the probability that 2 dice show the same number. Well, which one shows the same number? Like over here, 1 1, 2 2. Well, we don't see this, but 3 3 must be here. 4 4, 5 5, and right over here is 6 6. Correct? So 6 out of 36 in this case. So 6 out of 36. Once you reduce, it's going to be 1 over 6. The last one is calculate the probability that number on the red die is twice as large as the one on the green die. So do you see anything like that? Yeah, red die is, the number is twice as big. So which one is that? So for example, over here, 2 1. What else would be? 4 2. 4 2 and 6 3. There are only 3 cases like this, okay? Therefore, 3 over 36. That is 1/12 is the answer. Okay, let's continue.